Yep, so then you all can go ahead whenever you're ready.
Just to reintroduce ourselves, I'm Ella Sager.
I'm Cadence Foshi, but I go by Race.
And this is our asteroid farm.
This is the first picture, and then the next slide we decided to focus on, and we decided a lot of stuff on here in folders.
You got really quiet. Like I can't even hear you anymore.
Speak up, ladies.
Okay. In this picture, we think most of it was done by like space farming.
You might just need to individually get closer to the mic as you talk. That could be the only issue.
Where is it?
You know where your mic is?
Might be if it's a camera. This has got a little pop-up camera. It's very funky.
Oh, I can hear you. I can hear you just fine now.
Oh, okay.
Okay,
You just have to
you
use
can't,
two
I guess
buttons.
the thing is you have to project. You can't be shy and timid. Go ahead and go back to the last slide, the first slide there.
Easy. Use your teacher voice.
Yes.
This is the first picture, and the red outline is the next slide that we decided to focus on. And we decided most of the features on this picture, on this asteroid, were boulders, which are the blue. We figured most of it was done by, the shape was done by space weathering. And we think this particular lighter shade of the asteroid is from like high albedo. And we think like in the middle was a collision merge. So in the optional readings, it had a picture of Itokawa, which looks really similar to the first picture, which was formed by a colossal impact and had recumulation to form a rubble pile asteroid, which can show some of the reasons why there's a lot of bumpy places on the asteroid.
For this picture, we circled craters and ripples, and we think the ripples came from an impact that caused the surface to heat up, and both the craters and ripples are different sections that are in the next two slides. So we went off ordering the craters. We think the one with number 1 was the very first to happen because it's darker and has less defined edges. And crater 3 is on top of it. It's cutting it off. And 2 came next after number 1. And then 3 followed, and then 4. And we just went off how bright or how dull it was and how the edges looked or if they crossed over with one another.
And then going back to the ripples we saw, we think that the area on top of the crater, the dark area, is where the big impact was, which caused the surface to heat and create ripples down the asteroid. And then for the third image, there's not much to identify because we don't know the shape of the asteroid, but what we can identify is the boulders. And so again, the only thing to identify is the boulders, which had to come after the asteroid formed from past collisions and things like that. And that's our sources.
Okay, thank you. So yeah, this went a little faster than the moon pictures. Not a lot to say. Well, I mean, you can if you're really trying to, because that's what scientists who look at the geology of asteroids kind of, I don't want to say they make things up, but they have to get kind of creative in how they try to explain things they see. So let's go to the first one with Itakawa, the first picture. Like where you see the whole thing. Okay, so this is obviously littered with boulders of all, all kinds of sizes. But as you point out or don't point out, there was nothing on here that looks like an impact crater, right? And typically, when you see boulders, that indicates that something has busted up the surface, right? And the only thing that typically tends to be naturally are impacts, and those leave a crater. So where did these boulders come from?
They could have come from past collisions of other asteroids and meteorites or meteoroids, but also impacts directly onto the asteroid could have produced some rubble too.
Okay, all right. And are you saying that with that red box that it looks like it's like maybe two things that came together?
Right.
Okay. Yeah, and that's kind of thought. That's what happened here. So Itakawa, as you probably read, is probably what we call a rubble pile, or like you showed in the next graphic you have. So it's basically just the stuff just held together by their own gravity, just keeping themselves together. So it wouldn't be too difficult to go up to that thing with a spacecraft and disrupt it to the point where everything kind of starts coming apart, and then they would all come back together again, which is really weird but cool too. Why do you just ask, why do you see a bunch of boulders? Well, that's not what I want to ask. Are there likely large boulders like the ones you've circled? Are there likely large boulders like that? Let's just say subsurface, under the surface you can see.
Like covered by like the asteroid dust.
Are you saying like in the asteroid, like under the surface?
Yeah, like it's in its interior. Yeah.
I suppose if it's a rubble pile asteroid, then yes, it would have to be made of other pieces, boulders.
Okay. So I don't know. I was just curious what you thought. My guess would be that there could be some, but probably not a lot. Do you remember in the reading they referred to it was called the Brazil nut effect?
I remember that part somewhere.
Yeah. So this idea that I think a better analogy is like a bag of chips or a box of cereal. Like in a box of cereal or a bag of chips, where do you find all the little tiny crumbs and powder?
The bottom.
At the bottom. Why is it all at the bottom?
Because they can become really tiny and just fall through the cracks of the others.
So it's small and tiny in what?
They're small and tiny and they fall through the cracks like of space left by the bigger ones.
Okay.
Fall to the bottom.
So they're smaller than like the gaps between the larger whole pieces. And so they just work their way down to the bottom. And in doing so, which is not so analogous in a box of cereal, but to some extent, in doing that, they wind up filling in the voids of the bottom, so they push the bigger pieces up. And that's what we think is going on with asteroids like this. So over time, through small, medium-sized impacts, this thing gets shaken. And in doing that, all the very fine pieces, particles, what kind of looks like smooth areas, all those kind of start, getting shook down towards the middle of it. And that pushes all the bigger pieces up. So yeah, anyway, But just an interesting scale thing. The boulder on the right that you circled, there kind of looks like it's clinging to the edge of the asteroid. There was a back in February of 2013, an asteroid entered the Earth's atmosphere and exploded. It didn't hit the ground. It exploded over a town of Chelyabinsk, Russia. Did you ever hear about this, or have you heard about it?
It was in Russia.
Yeah,
I think I've seen a video of that. Maybe.
it's possible because there are a lot of like people's dash cam videos from their cars that captured it because it was like kind of early in the
Yeah.
morning.
I remember that.
Okay, so that asteroid was about the size of that boulder. Now it exploded in the atmosphere because of friction. Friction from the atmosphere heated it up and broke it apart and exploded. But then that resulted in an airburst that just all that energy then just propagated through the atmosphere down to the ground. It still caused a lot of damage. So even if you don't have an asteroid that hits the ground, you could have something explode in the atmosphere and still do some significant damage to stuff on the surface. A similar thing occurred in 1908 over Siberia. It's called the Tunguska event. If you look that up, you'll see like black and white photos of it, of the aftermath, and like the forest that exploded over, all the trees are all like laying down flat radially from like a center point. And that's the same thing that happened there, probably an airburst of an asteroid. So there are two events like that occurred basically within a century of themselves. So these things are out there. They're hazardous or potentially hazardous, as they call them, PHAs, potentially hazardous asteroids. So the DART mission, you've heard of the DART mission. Okay, so it did its impact of the asteroid at the end of September. It was successful. It did exactly what they'd hoped it would do, and that was a planetary defense demonstration. So anyway, all right. Next one, Vesta. Okay. So yeah, basically there's just craters and some ripples on here. So impact crater, of course, a geologic process happens on all solid surfaces in the solar system. And those ripples are a result of an impact. Like you said, there's a really huge crater. I think it's North Pole area of Vesta. It's called Rhea Silvia. When the impact occurred, it just made the ground ripple like an earthquake, really. But on Vesta, I noticed that's still preserved, those shapes. So yeah, not much to say there. I don't know if you read the three craters that you circled there. They call that the snowman, I guess for obvious reasons.
I did that the other day.
Did you? Yeah.
Yes.
That's what they call it. All right, next one, final one. Yeah, so even less to talk about here. This is from the asteroid Eros, E-R-O-S. Also a rubble pile, likely. Its shape was actually fairly similar to Itokawa, although it kind of looks more like a dog, like a cartoon dog bone, but with only like one end has the little knob on it, the other end is just kind of straight. Anyway, so yeah, it's the same thing. These boulders, I mean, you can kind of tell some of these boulders, particularly if you look to the largest one that's to the left of the one that you circled on the bottom. If you go to the one toward the left, there's a grouping there. Yeah, that one right there, that looks like it's partially buried, right? So it's just another thing of where these larger blocks rising up out of the finer regolith from that Brazil nut effect. As just a sense of scale, I didn't give you scale bars for any of these images, but the largest boulders, including like the ones you circled, two of the ones you circled, those are about the size of a house. So this is kind of like looking down like on a neighborhood, kind of. That's the whole area of the image itself. So yeah, messy. All right. Well, good job. Very good.